Hello,
Hello.
everyone. Well, let's wait 2 more minutes so everyone can join, and then Julio will start with the workshop.
Before we get started, congratulations for all the Argentinian fans to reach the final yesterday. That was one of the best matches I ever seen in my life.
Yes, we are all recovering from the stress. Okay. So I think we can start now. So go ahead.
Perfect. First of all, good afternoon, everybody here. This workshop is called Agentic Coding Patterns, the hidden infrastructure. Please, laptops open. We're going to be building things. Okay, it's not going to be the classic, like, I'm just going to talk or show things. No, I want you to participate with me. Okay, so this is going to be a dynamic. Okay, so first of all, who am I? Next slide, please. And why am I doing this? Well, my name is Julio Lugo. I know that many of you have already met me in Buenos Aires, or Anthony, who met me like 10 years ago. I'm a software engineer here at Biontech, but I'm also a Magister Scienziae candidate at Georgia Tech. But besides that, I'm also another Vibe coder, one of these guys who fell in love with the fact that I could generate code, but I had to learn my lesson in the hardest way possible. And I'm going to talk about that just in a minute. And my goal today is that you don't commit my mistakes, because believe me, the path that I had to go through to learn a lot of things that I would love to be taught in the past is the reason that I'm quite motivated to give you this workshop today. Next slide, please. Now, this is some sort of a story because I fell in love with vibe coding, and my fall, to my disgrace, started with an illusion. So I believed that vibe coding came in to be my savior and would reduce my stress and lower back pain, because believe me, this chair is beautiful, but it's hard. It's hard to spend 6 hours here. But believe me that it was not what I thought. Yeah, I know. Just came in, open Claude, and typed some base prompt, shipped a fast demo, and I had rapid results. And at the end of the day, live coding is basically generating a lot of code, leverage on its generative capabilities with minimal planning, weak verification, and zero engineering infrastructure. And yeah, you feel like you're a magician. You feel like everything is just so fast until you see below the waterline and you notice that your project is literally collapsing under its own weight. So, next slide, please. When the project collapsed, the reality hit me with a bat, for real. Yeah, coding with intelligent agents is an engineering practice. At the very beginning, I didn't believe that. It's like, this is impossible. I mean, I'm just generating code. I'm using it. I should be the engineer, but no. Using agents, it's part of an engineering process. And here's where I will start. This is going to be a phrase that will mark our way to think. Verification beats confidence. So if you notice this, you have at least 5 nodes that you could consider like fundamental in terms of agentic coding. Specification engineering, so you need to know what to do. CI/CD pipelines, because you have to understand that whatever you're working on, it's to be integrated and delivered as a product. Execution guardrails, because you have to make sure that your work or your generated code is not going to break other people's work, or you're not going to be breaking other people's systems. Context management, because you need to understand that it's not just about the guardrails, because other people, yeah, they have to protect themselves, but you have to understand where you have to work on and why it has to be like a limited sandbox. And we will be talking about sandbox in a minute. And finally, you need to understand that verification engineering is literally one of the most important steps that we are constantly missing when we are vibe coding. So these 5 nodes can be described in 3 points. Systematize inputs. Every single time that your coding process begins, specifications and context must be engineered, not just guessed. Second point, automated guardrails. Yeah, you have to make sure that you're not going to break other people's stuff, but you have to make sure that you're not literally paying attention to it manually. You have to automate those processes through CI/CD pipelines, for example, that would stop a roach agent like in real time. And finally, continuous verification, which means, as I said, verification beats confidence. You have to make sure, every single time that you're generating code, you have to make sure that your code is tested. But yeah, it sounds pretty obvious, right? Those are like the kind of things that you can read literally in a single article, Medium article. You can read it maybe in a book. But my workshop is not going to be just here. I'm going to, let's say, one step ahead of that. Let's go with the next slide, please. Now, let's talk about what are we doing right now. Let's do a systematized way to understand where are we right now? Where do we stand? So there's a capability matrix to understand what are we doing right now. So we will identify ourselves, what kind of engineer, what kind of vibe coder, or what kind of in the middle we are. So there are 3 levels: vibe coder, transitional coder, and agentic engineer. And you can see 4 different skills that you can consider, like, okay, so I can measure this and understand where am I. So if you're literally ad hoc prompting, like you just type something to solve a problem, but without a real structure. If you have 0 organizational memory, like you're writing it down to see whatever's going to happen. When you open, with codecs like unrestricted access, and you can modify whatever you want. And when you just go and say, okay, this looks right, I'm just looking at the code, it looks so beautiful, yeah, cool. Believe me, you're a vibe coder. You're literally level 1. You're a rookie in terms of agentic engineering. Then there's a second level, which is a transitional level, where you can say, okay, so you have a structured prompting. It's like, okay, it's not the classic pre-shot, but you have like a few shots. You're trying to point something. You have a structure to solve things. The context is limited, and you try to manually update it whenever you need it. The execution is restricted, yeah, through its basic tools. And finally, you try to verify, at least with manual testing and basic unit tests. Most of us, we fall in that description. But to be a real agentic engineer, you need a 1 step ahead. Minimum specs and reusable templates. Oh, the prompting now is a template. Now it has to be something that you pass to the model. Then you got the context. Oh, version controlled knowledge hubs. Oh my God. So you need to actually define what the agent's going to do, not just in your run, but also every single time that the agent's going to run for every single project and for every single task. For example, you have multiple projects, you have to define the way that the agent is going to behave in that specific project. So you have a controlled context. The execution, oh, you don't just open your laptop to do it. You actually try to build a sandbox. So every single time that the agent is going to be working, it will be controlled within a sandbox with strict tool orchestration. And finally, in terms of verification, as I said, verification is one of the most important things here. Automated verification pipelines and governance gates. Okay, we got a matrix. And I would like you to think, where do you stand in terms of this capability matrix? Now, let's go with the next slide, please. Yeah, this concept of agentic engineering is quite deep. As I said, you know where you stand right now because we understand the capability matrix. But now we want to go from like a transitional engineer, from a rookie vibe coder, but we want to be an agentic engineer. We want to be that. But how do we learn all those concepts? How do we find all that knowledge? And how do we learn it like in the fastest way possible? Well, let me tell you, there is a framework for that. The framework was done by Professor Jonas Montilva, which is a professor at University of Los Andes. Vale has just shared with you the paper where he explained this concept that I will refer as MOSAT, which is an ontological and systemic method for the conceptual learning of digital technologies. The paper is in Spanish, but you can translate it with Google. Basically, he uses systems theory to analyze any tool, anything, through 3 dimensions: discipline, process, and product, using structured questions to generate text summaries and visual diagrams. So we are going to be using the way that Professor Hanas explained his technique to learn new digital technologies, to learn new skills, and we will apply it to understand agentic engineering in a systematized way so we can apply those, but using a coherent knowledge base. Okay, so that's what we're going to do now. Next slide, please. So how does this framework work? Okay, well, software engineering is not the same as traditional engineering. So to understand how to build reliable AI systems following MOSAT, which is the framework I just described, we must build our infrastructure through 3 complementary perspectives. Technology is a discipline, as a process, and as a product. So modern software engineering is undergoing a profound transformation. Okay, this is a reality. For decades, engineers learned how to design, build, test, and maintain software systems created almost entirely by humans. Today, however, intelligent agents are becoming active participants in the engineering process. They can reason about requirements, generate implementations, execute tools, write tests, review code, and even document entire projects. So this evolution raises a new engineering challenge. Listen to this question. How do we design systems in which humans and intelligent agents collaborate safely, reliably, and continuously? Because we want engineering products. So the answer cannot be found by studying tools alone. So you go to Cloud and Codex, and you won't find a real answer for that. Individual projects, such as, well, as I said, Cloud Code, Cursor, Codex, or future AI systems will inevitably evolve. But the underlying engineering principles should remain stable over time. So this is precisely why we adopt the MOSAT framework. Rather than describing agentic engineering as a collection of products and all that stuff, we don't want to go that way. We want to have something conceptual that we can use for every single technology that will come in the future. So Mossad allows us to understand it as a complete digital technology through three complementary perspectives, that's, as I said, as a discipline, as a process, as a product. Okay? So as a discipline explains the body of knowledge behind the technology. As a process explains how engineering work is performed. And as a product, which explains the tangible engineering infrastructure organizations build. So next slide, please. Let's talk about discipline. So you will see this figure here, right? We will be describing it. Okay, so I will go through the entire graphic, but let's start at the very, very center, okay? The execution core. We will be talking about that. So designing before code, that is literally the most important thing you have to do. It's designing. It's not about coding. That's not the problem anymore. It's design. So specification, engineering, task composition, and persistent knowledge architecture. So you have to make sure that everything is done before coding. Boundaries and control, as I said, yeah, we need some guardrails. We need to make sure that we're not breaking other people's stuff. So we need to have isolated environments, such as using sandboxing, specialized sub-agents, and objective exit metrics. And the third one would be validation, assurance, verification, where we basically establish a fact. Verification precedes trust. Continuous validation to guarantee real business value. So before an organization can successfully build software with intelligent agents, it must first understand the engineering knowledge that governs them. From the Mossad perspective, technology as a discipline represents the conceptual foundation of a technology. The body of principles, methods, concepts, and engineering practices that explain how it works independently of any specific implementation or AI model. So in agentic engineering, this body of knowledge is represented by what we call the hidden engineering infrastructure. And here the title came in. While developers and stakeholders usually see only the final application, every successful agentic system depends on an invisible conceptual architecture that guides how work is performed. The quality of an agentic system is therefore determined less by the intelligence of the underlying language model and more by the engineering principles that organize and constrain its behavior. So, as I said, the blueprint that we have here illustrates the conceptual architecture as a series of concentric layers. So at its center lies the execution core, representing the intelligent agent responsible for performing engineering tasks. Surrounding it is the pre-execution layer, where engineering begins long before any code is generated. Specification engineering transforms business objectives into executable requirements. Planning and task composition organize complex problems into manageable units of work. Context and retrieval engineering provide agents with the information required to reason correctly, while knowledge architecture defines how organizational knowledge is represented and preserved. The next layer, right, establishes the engineering boundaries that govern, and this is an important word here, the governance of the product, that govern autonomous behavior. Sandbox and execution environments allow experimentation without risk in production or critical systems. Specialized agents divide responsibilities according to expertise, while quality gates define objectives criteria that determine whether work may continue. Rather than restricting intelligence, these boundaries enable autonomy to operate safely and predictably. And now let's go with the utmost layers, are the verification and validation. So here, software is evaluated through objective engineering evidence rather than subjective competence. As I said, verification precedes trust. That's the way you have to see it always. So again, and the validation will basically this layer connects engineering with business value, stakeholder needs, ethics, and organizational objectives. So taken together, right, these layers define the intellectual foundations of agentic engineering. So we got an entire intellectual framework for everything that represents this transition from the classical software engineering to agentic engineering. So they establish the conceptual vocabulary through which engineers think about specifications, context, autonomy, governance, verification, and value creation. Next slide, please. But as I said, guys, this is not going to be something like just me talking. No, no, no. I want you to play a little bit with me. So this is going to be our first laboratory. So from the previous slide, select one foundational component, right? Maybe complex engineering, sandboxing, and deconstruct it before you use it. You can use the following boards that you have here, following cards, and you can make your deconstruction, or you can make your analysis. See you in 5. 'Vale, can you show the previous slide, please?
2 minutes left.
Okay. Um, well, I'll give you one quick concept from this um, slide, and it will be word rails and safety, for example. So the definition, simple, intentional restrictions, operational controls, and boundary system placed around AI agents to prevent unauthorized actions and destructive operations. Purpose, to prevent catastrophic failures by ensuring AI operates strictly within safe, isolated environments, sandboxing, and cannot execute high-risk commands. Components, approved tools, forbidden tools, execution isolation environments, and approval gates. We will discuss that with the canvas that we will discuss in the future. Relationships. Rails are essential prerequisite for execution and tie directly into the verification engineering and CI/CD integration. Examples, revoking an agent's permission to run data definition language operations like drop database or requiring human approval before modifying authentication systems. And finally, misconceptions. To believe that an AI model will know better than to delete a database, treating the AI as an autonomous programmer rather than a component that needs strict engineering governance. Next slide, please. Okay, so as we said, we were discussing three pillars. This is the pillar number 2, technology as a process. This is not ad hoc prompting. This is very important. This is the way we are going to be like leaving that old knowledge behind. You're not literally just writing cloud, hey, please, what do you think about solving this in that way? No, no, no. It has to be something that follows a structured way to build. It's not just like, okay, as I said before, the prompt is structured. No, it's not just a structure. It is a process, okay? So while the discipline explains what agentic engineering is, the process explains how it happens. So from the Mossad perspective, the framework, technology as a process describes the structured transformation through which human intent becomes validated software and ultimately organizational knowledge. So unlike traditional views of software development that emphasize coding as a primary activity, that was in the past, of course, agentic engineering recognizes that reliable software emerges from a repeatable engineering lifecycle. Code generation is only one stage within a much larger process. So we got 3 clusters here, right? So you can see in the figure. So the first cluster is a pre-flight lock. It's just like an aircraft, right? Imagine an aircraft. So an aircraft performs extensive checks before leaving the ground. Every agentic project begins with preparation rather than execution. So engineers define specifications, establish objectives, identify risks, decompose work into manageable tasks, and retrieve the knowledge required for successful execution. At the end of the stage, the organization possesses an executable engineering plan rather than merely an idea. Okay, so that's like literally the very first step. Specify, plan, and retrieve the context are like 3 steps inside our first cluster. So the second cluster is the execution loop. Okay, in this loop, intelligent agents perform engineering activities through continuous iteration. So the execution is never treated as a one-shot event. So forget about it. There's no magic here. Instead, implementation is immediately followed by a verification and review, creating a feedback loop which defects and in which defects are detected early. Okay, assumptions are challenged, and solutions gradually converge toward higher quality. So this loop transforms software development from isolated code generation, right, to continuous engineering refinement. As you can see, you execute, you verify that whatever you are executing is correct. And if that works, you review it, and then you go back to execute. That's the loop. That's the feedback loop that we're talking about. So, and the final cluster, the output track. So once software satisfies both technical and business requirements, the engineering process continues by documenting architectural decisions, updating organizational memory, refining workflows, and improving reusable engineering assets. So about engineering assets, we'll be discussing right in a moment when we were talking about the product perspective. So every completed project, therefore, leaves the organization more capable than it was before. It's one of the most important things. So you document and then you iterate. You do it again and again and again. So every single iteration, the business, the organization, the company be is gonna be better than before. Okay. So this life cycle emphasizes that the true output of engineering is not only work in software, but also accumulated organizational capability. Every iteration contributes new knowledge, stronger verification strategies, and more effective engineering practices. Okay, next slide, please. And the third, oh, no, there's no third yet. We go with the second laboratory. This is 2 minutes, so super short. Okay, so let's suppose that we have this prompt below. Make a secure login page for our path that connects to the database. And then you get Claude or Codex or whatever with a result that is basically super vulnerable and has technical ambiguity. Okay, so I would like you, 2 minutes, proceed writing down some personal engineering specifications. Okay, I just know that it says 5 minutes, there are 2 minutes. Okay, so I'll give you this template here so you can create your engineering specifications correctly and have a good prompt. Okay. Guys, if you want, you can share your ideas through the chat. Okay, so you can start discussing about it. You can make jokes about it if you want, but let's do it. 2 minutes. Okay, so super quick. We want to prove it. So first thing we need to understand assumptions. Database schema already exists. The required context for the database connection is located in the organizational knowledge repositories. Strict constraints. Easily, the agent must stay strictly within scope and prefer minimal incremental changes. Verification criteria before completion. Execute all relevant tests, report the executed commands and their results, and summarize the code diff. In terms of reproduction parameters, We could say something like maybe recommend, I don't know, recommend documentation, updates for agents, and cloud to record new logging components, something like that. You can think about it. In terms of the objective, if you want to say, implement a secure front-end login interface and connect it to the existing authentication backend. Before making any changes, the agent must summarize this objective, propose a step-by-step execution plan, and identify relevant files. So it could be an option. Next slide, please. And we go to the third pillar. Okay. So third pillar is technology as a product. Okay. So here, the final Mossad perspective focuses on what organizations ultimately build, rather than viewing agentic engineering as a coding assistant or an AI-powered IDE, which is not. Technology as a product defines it as the complete engineering platform that enables reliable collaboration between humans and intelligent agents. So the most important shift in the perspective is understanding that software itself is not the final product. Instead, software becomes one of many outputs generated by an engineering platform whose primary purpose is to accumulate reusable engineering assets. So this is very important. Agentic engineering is about producing reusable engineering assets. Okay, so the first category of assets, yeah, is knowledge assets. You can see it there. So these preserve organizational intelligence through architecture documentation, engineering playbooks, coding standards, agents LMD files, cloud LMD project memories, design systems, and architectural decision records. Together, they ensure that both humans and intelligent agents operate from a shared understanding of the project. I've also seen wikis, for example. The second category consists of execution assets. Okay, so these execution assets operationalize engineering work through sub-agents, orchestration mechanisms, execution hooks, context retrieval systems, NCP integrations, CI/CD pipelines, automation workflows, and sandboxed execution environments. So these assets transform engineering intent into reliable execution while maintaining consistency across projects. And finally, assurance assets, because they provide the confidence required for professional software engineering. Okay, it's literally the quality product. So verification pipelines, governance policies, quality gates, approval workflows, audit trails, observability platforms, and engineering metrics guarantee that every engineering outcome can be verified, explained, reproduced, and trusted, which is like the final step. Unlike traditional software projects that conclude when a feature is deployed, agentic engineering products continue to evolve. Every execution enriches documentation, improves workflows, and strengthens governance, and expands the organization's engineering memory, right? And over time, well, the platform becomes increasingly capable. Next slide, please. And here is our lab 3. 2 minutes again. So this is going to be individual, right? You can do it on your own. It's basically, you can map an engineering architecture onto your current team's code base. Okay, you can do it super quick. Do you have memory system? Where does it live? What APIs can it touch? So is it integrated with your code, right? Your LLM, something like that. Do you have quality gates to verify that everything that you are coding, like generating, is actually correct? And finally, what is explicitly forbidden? So we will talk about data governance here. So 2 minutes, we'll be back. Okay, so what do we have here? So this is a solution. So in terms of the context management and memory, so in my case, the system utilizes a knowledge architecture where organizational memory stored in cloud.md, for example. So it provides agent with the exact uh, specifications and instructions, security protocols before it takes actions. In terms of orchestration, so we have a part that's like literally AST dash grep, which is to identify different patterns. And the architecture strictly separates those files which are strictly read-only from the rest of the right tools. Okay. CI/CD integration, yeah, to in terms of the verification, right? Uh, in this case, we do have some automatic security tests, right? We've seen grep, for example, is the one we have, but we also have static analysis, and which makes sure that we are actually following the correct coding standards. So we make sure that we are not literally merging some trash. Um, and in terms of governance, we do have sandbox execution isolation. Okay, so of course it cannot deploy to production. It cannot literally push. It has to go through the proof of gates, and of course the human intervention is always present. Okay, so we have trajectory review and exit criteria for that. Yep. Let's go with the next slide, please. So we have talked about um, what is what are the three pillars. So we have talked about Mossad and we have talked about all of this stuff, but we want to establish literally like big picture of how the agentic engineering should be seen. So in this scenario, we will be discussing the operational controls, which are the pre-flight, the execution, the post-execution, and the master prompt, which is basically how are we going to take that schema, that theoretical concept, and how we're going to put it within a prompt. So prompting is often misunderstood as asking an AI to write code. That's the problem. In agentic engineering, prompting is better understood as establishing an engineering protocol that guides how an intelligent agent approaches a problem. So the goal is not to maximize code generation. Bullshit. That's not the real reason. But to maximize engineering quality, we have to focus to quality. So a well-designed master prompt standardizes engineering behavior across projects by requiring every execution to follow the same disciplined workflow. So before beginning an implementation, as I said before, the agent should understand the engineering objective, identify assumptions, inspect the relevant context, propose an execution plan, and identify potential risks. During implementation, it should remain within the approved scope, minimize unnecessary changes, respect organizational constraints, and continuously verify its work. Yeah, this is literally engineering work. This is what we do. But now we have to be with the agent, literally like a child. We need to make the agent know that these are its constraints. These are the guardrails that they cannot pass. Okay? So before completing the task, it should execute all required validations, summarize the implemented solution, explain any remaining risks, and recommend updates to the organization's engineering knowledge. So this protocol transformed prompting from an isolated conversation into a repeatable engineering methodology. A simplified version of the protocol can be summarized as follows. Okay. Understand the problem before proposing a solution. Plan before implementing. Retrieve context before reasoning. Execute only within approved boundaries, and verify every engineering decision, and finally document what was learned for future projects. Very similar to what we understand within the process view, right? So when consistently applied, the master prompt becomes more than instruction because we take these operational controls, we build the master prompt, and it becomes more than just an instruction set. It literally becomes an expression of the organization's engineering culture. Okay, so summary: the master prompt standardizes how intelligent agents think before they act. Next slide, please. Now, this is our final app, right? 2 minutes. So we got an AI generated migration script compiled perfectly, but dropped a production table. I want you, engineers, diagnose the structural failure based on what I've just said. 3 questions. What infrastructure was missing below the waterline? Which missing governance control on safety gate allowed the failure? And finally, what organizational knowledge, for example, cloud, must be updated to prevent recurrence? Guys, please, I understand that there are a lot of people trying to chat with us, but please try to interact through the chat. I'll encourage you to do it. I want it to be, some discussion space, please. Like, I know this guy's just talking a lot of bullshit, so you can write it down if you like. But please, come on, let's interact. Yeah, Vale, can you put the previous slide, please? Okay, let's go to the next slide, please. Super quick. What infrastructure was missing below the waterline? Easy. So it initially it showed fast results and likely produced a working demo of the login page right before the final crash occurred. Yeah. But what was missing is because it lacked the hidden infrastructure. There was no sandboxing. There was no execution isolation. There was no operational controls in place, right? So it is terrible. So next question is, which missing governance control or safety gate allowed the failure? Well, the critical missing controls were the guardrails on safety and forbidden tools. The agent was given unrestricted access to the database environment rather than being constrained by an approval gate or restricted permissions. Furthermore, a lack of exit criterion quality gates allowed the destructive code to execute without a trajectory review. And finally, what's the organizational knowledge? Well, to capture the lesson, the organization must update their agents.md file to permanently classify database deletion commands under forbidden tools and mandate execution isolation for all future database-related tasks. This ensures the failure builds the team's engineering capability rather than just fixing the code once. Okay? So those are like the things. Next slide, please. Now we got everything everywhere all at once in this beautiful slide, which is the Agentic Foundation Canvas. I know Valentin is going to share with you one beautiful version of this that you can use. You can rewrite as you wish, which is basically a way to design agentic systems before writing code. This is like literally the template. So specifications describe an individual engineering task. The Agentic Foundation Canvas describes the engineering system that will perform it. It serves as the architectural blueprint that every agentic project should complete before implementation begins. So it's inspired by engineering design canvases rather than conversational prompting. The Foundation Canvas forces teams to explicitly define the information that intelligent agents require in order to operate safely and effectively. The canvas begins by defining the expected visible outcome. You can see it right there. It's literally left upper corner, okay? Okay, establishing what success looks like from the perspective of users and stakeholders. It then captures the minimum specification, describing the essential functional requirements and engineering objectives while identifying the primary failure risk that could threaten the project. Once the objective is clear, the canvas defines the operational context. Engineers identify the required context that agents must understand before execution, the proof tools they may use, the forbidden tools they must avoid, and the execution environment in which engineering activities are allowed to occur. The final section establishes engineering assurance, okay? Teams specify the required tests that demonstrate correctness, the approval gates that define human oversight, the required evidence that must accompany every implementation, the knowledge destination where the lessons learned will be documented, and the CI/CD strategy that integrates the work into the organization's delivery pipeline. So by forcing these decisions to be made before execution begins, the Agentic Foundation Canvas transformed software development from reactive coding, from vibe coding, into intentional engineering design. So most importantly, the canvas reinforces one of the workshop's central ideas. Engineering begins long before the first line of code is written. The Agentic Foundation Canvas is therefore not simply a planning worksheet. It is the architectural blueprint through which organizations transform ideas into engineering systems capable of producing reliable software again and again. Next slide, please. Now, believe me this, to write code faster once, yeah, that's the short-term solution that I felt. I declare myself guilty. Yeah, speed in a single instance does not scale, creates localized efficiency, but fails to solve systemic bottlenecks. It is true. What is our ultimate goal? Build an engineering capability that continuously improves. True value is created when systems and teams learn, adapt, and evolve through constant interaction. So this workshop ultimately presents agentic engineering as a complete engineering framework rather than a collection of AI tools, as I demonstrated. So through Mossad, through this framework, we learn to understand the technology as a discipline, as a process, and a product. Through operational controls, we establish the governance required for safe execution. Through the master prompt, we standardize engineering behavior across intelligent agents. And finally, through the Agentic Foundation Canvas, we design the engineering system before implementation ever begins. So together, these artifacts represent a single philosophy: engineering before prompting. So every successful agentic project begins with knowledge, proceeds through disciplined engineering processes, operates within governed execution environments, and leaves behind reusable engineering assets that strengthen the organization over time. So if there's is one message that you guys, that for real, you should remember after this workshop right here, right now, is this one. Agentic engineering is not about making AI write more code. For fuck's sake, believe me, it's not about writing more code. It is about engineering systems in which humans and intelligent agents collaborate to continuously produce reliable software while compounding organizational capability. I honestly think it gives you a complete, coherent wow workshop. Yeah, definitely. Has the clear beginning, where should we start, and the foundation canvas, where what should we do. So yeah, it's not like the classic AI techniques and all that stuff, but I understand that it should feel for you like the introduction of a genuine engineering framework. That's what's the idea. So next slide, please. 2 minutes for questions if you have one, but I noticed that you didn't say a thing in the chat. So, well, I will assume that it was super clear, that there was no confusion, that everything was like crystal clear, that you will be a fantastic agentic engineers after this. So I really, really, really love you guys. Thank you. Oh, Antonio, tell me.
Hello, guys. Yes, I wanted to ask. I don't follow that particular kind of architecture for managing kind of the context, the memory, and kind of the word rails for the code base. But I do use some skills similar to the Matbot ones that you basically kind of always discuss with the AI, kind of what are the explicit requirements and limitations on what the code base should be. So basically architecting the features. Would that approach, like asking the AI, okay, here are the things we developed, here are the code base. Let's discuss about what rails, for example, basically building the architecture that you suggest. Would a skilled would be useful, for example, to have that kind of setup, like for
Yeah,
example,
definitely. Yeah,
you can build like a skill that says let's build the architecture to have these guidelines hard hardened basically.
yeah, because it is directly a product. So, for example, if you are defining a guardrail, this is what I understand. It's like, okay, I want you to let's discuss potential guardrails, and you start discussing that with the AI. You're proceeding initially with an engineering process because you're designing the guardrails. You're using the AI to say, okay, so this is what we have. This is the code base we have. How can we start constructing the guardrails? So you're following the correct steps. You're designing. You're in that pre-execution step where you're literally okay. So it's time to understand what we want. Then, if you use that knowledge and you apply that knowledge to start an iterative process with the agent itself to build guardrails for a bigger system, for example, that is a good way to use it. So yeah, totally, it's a great way to do it.
Nice. Is there any skills available online that you could suggest that can help to kind of modify kind of the context files to be better shaped in the similar way that what you suggest on the workshop?
Yeah, I mean, there are, if for example, it depends on the AI model that you use. There are several um, cloud code skills, for example. There's this literally one that is, I don't know, like one of the most um, famous, which is superpowers, and most of you are probably familiar with it. But it's one of those that actually tries to follow this kind of theoretical concepts. For example, it uses test-driven development. It refuses to write implementation code before failing tests exists. Locks in architecture before touching the code, for example. So superpowers is one of those tools that I would definitely recommend to everyone that's going to be working with cloud code. I'm going to share the link over here.
Thanks.
Okay, so well, thank you, Julio. This was great, and thanks to everyone who joined. I'll be sharing the workshop recording in the Agentic Foundation Canvas template shortly. So yeah, thank you. See you in the next one.
Thank you, guys. It was a pleasure for me to be here.